Hello and welcome to today's webinar, OS-VVM, the leading edge verification for the VHDL community. This is the first part in our four-part series of webinars on better FPGA verification with VHDL. I'm your host, Nomita Goswami, an application specialist at PerCDA. LDEC has been leader in the EDA industry since 1984. The company delivers innovative design, creation, simulation, verification, and prototyping solutions to assist in the development of complex FPGA, ASIC, system-on-chip, and embedded system designs. In today's webinar, we are going to provide a broad overview of open source VHDL verification methodology, also commonly called as OS-VVM, and its capabilities. We have a question and answer session towards the end of this webinar, and we invite you to submit questions using the question panel on the right-hand side of your screen. We would also like to let you know to expect emailed instructions after this webinar to view an online recording of today's presentation along with today's slides. Well, today's guest presenter is Jim Lewis. Jim is chair of IEEE 1076 VHDL Standards Working Group. He's co-founder of open source VHDL verification methodology that we are talking today. And he is also a chief architect of its packages and the methodology itself. Jim is also an expert VHDL trainer for ThingWorx Design INC, and he has about 30 plus years of experience in design and teaching. In his design practice, he has created designs for print servers, IMA E1, T1, networking, fighter jets, video phones, and spacecraft. Hi, hello, Jim. Welcome.
Hello, happy Thursday, everyone. Thank you, Nomita. So I'm here to talk to you all about OS-VVM. And we're going to start out with where is VHDL's place in things, because we hear a lot of things about SystemVerilog, this and that. And what I'm going to say is there's nothing to be concerned about, but we'll see that in a minute. Then we're going to talk about what is OS-VVM and its framework and our verification components. And then we're going to follow through a whole flow of testing with OS-VVM. We'll get down to the test reporting. We'll talk briefly about the scripts and then where to look for other stuff. Okay. Again, my background, I have a substantial amount of VHDL background, about 30 years. I've been active in the VHDL working groups, the IEEE VHDL working groups for over 20 years. I've been the VHDL chair for 14 years. I am the chief architect of OS-VVM. I'm a consultant trainer for ThingWorx. ThingWorx, we're a VHDL training company. We provide 3 of flagship courses, and of course, we do customizations for customers. Okay, and I think this is what makes OS-VVM special, is because of the depth of background of VHDL and the level of expertise that's brought to the table. And it's not just me, it's some of my colleagues from the working group that are doing donations here and there too. Okay, so VHDL's place in the world. If we look at its market, which is FPGA, for FPGA design and verification, 64% worldwide use VHDL. 84% in Europe use VHDL. For verification, 50% worldwide use VHDL, 72% in Europe use VHDL. Okay. With respect to OS-VVM, worldwide, 18% use OS-VVM. If we look at just the VHDL FPGA users, then it's 36%. Okay. In Europe, 34% use OS-VVM, while only 26% use SystemVerilog and UVM. Okay, so that's an interesting marker there too. So in the FPGA space, especially in Europe, SystemVerilog is not the thing. Okay, and so what is OS-VVM? Well, to really assess that, we have to look at all the different pieces. It's a verification framework in which we define a transaction interface, API, verification components, and a test sequencer. And when I say the methodology defines this, other folks are using the words standardized. So you could say we have an internal standard, because that's exactly what other folks have. Other methodologies have internal standards, but nobody has done any consensus-based standard on anything at this point. We have a verification utility library that is what gives OS-VVM a lot of our capabilities. So like our constrained random, our functional coverage, our scoreboards, our alert log mechanism, this is all coming from the utility library. And then we have a growing set of verification component library that includes our AXI family, our UART, and we're working on additional things too in the background here. And the other thing that's really grown up over the last 3 years or so is our tool independent scripts. Our goal is one script to run them all, make it easy, run right down to code coverage the same way in different vendor tools. Okay, so benefits of OS-VVM, it simplifies writing test cases and verification components. We'll see a little bit of that today. It makes tests readable and reviewable by all. And you know, when I say that, people are like, there's a gap between verification and designers, but there shouldn't be. And I don't think there is when we look at test cases with OS-VVM. Going further, your software and system engineering team should be able to review them too, because hey, if they're subjected to a review, I sure would like to get useful feedback from them. Okay, we have powerful reporting. We have HTML for humans to look at, and we have JUnit XML for your continuous integration tools. We've built features at this point through the upgrades that we've gone through actually over the summer of 2021 that make our constrained random, our scoreboards work as if they were built-in language features. If you're using the older interface, the protected type interface, you can still use that, but I encourage you to check out the singleton interface, which I'll be talking about briefly today, but in more detail in the fourth webinar. Okay, and you can adopt OS-VVM incrementally in your current VHDL test bench and verification components. It's not all or nothing. Okay, so you can dip your toes in, start using the alert log capability and grow from there. Okay, so OS-VVM's history, very briefly, we started in '97. That's when I started formalizing training under ThingWorx, and I started teaching the framework because the framework really grew out of some consulting assignments I was doing, and grew up there, brought it into the training class, and then we started adding to it. We added the randomization and the scoreboards to it, and we added the coverage to it, and then we added, rather late I might add, the alert log package capability to it. And you know, as things started falling down the OS-VVM track, that's where we were open sourcing things. Many of these things we introduced in our training classes first. Okay, you can see there was probably a 10-year difference between when we shared our scoreboard package with everyone. Okay, and likewise with our utility libraries. Our TB util package was something we held private for quite a long time. 2018, we started to get serious about adding verification components. 2020 with the shutdown, you know, I normally travel 75,000 miles a year. So suddenly I had this extra time on my hands because we're doing all our training online at this point. Okay, so there we got serious about scripting. We added specification tracking. We added the model independent transactions, which we'll see a little bit of today, virtual transaction interfaces, which we'll see about in the next webinar. And we added bursting and other capabilities and evolved. In 2021, we evolved how we do the bursting a little bit because we added the singleton data structures. That was a big, big add, and it makes things, it allows you to use these as a normal procedure and function call API. All right. And this year is when we added the HTML and JUnit XML reports. So if you haven't seen the reporting recently, you're going to see it today. I'm really excited to show it to you too. So when we look at the OS-VVM framework, it really looks identical to the same way SystemVerilog draws their framework. Okay. We have verification components that implement the signal interface signaling, but in OS-VVM, it's an entity and architecture rather than being class-based in SystemVerilog. That makes it closer to what the RTL community understands, okay? In fact, it might be easier than what they understand, because RTL, I think, is harder than the test bench behavioral code. Okay, and then we write our test case inside architectures of test control. This is where we do the sequencing of what's going to happen on our system. Okay, so we have a single point of focus for sequencing our test, and then each test case is a separate architecture of this. And this is the one place in our flow where we separate the entity and architectures. Okay, if we look at the verification framework and some synonyms for this, in the verification space, we call it a test harness. In RTL code, you called this structural code. If you did gate design in the past, we called this a netlist. Okay, so really, this all plugs together just like RTL. We instance our dot, we instance our verification components, and we instance the test sequencer. Not a lot to this. Some like to say it plugs together like Legos. Yeah, that's exactly it, but that's exactly how RTL works. Okay. Now, if we look at the elements of OS-VVM verification framework, we have a transaction interface. That's our record here, connecting our test control and our verification components. We have our transaction API. That's the set of subprograms for a given verification component that we can call. We have our verification components, and we have our test sequencer. Okay. So our transaction interface in OS-VVM is record-based. This is something that was legal in '97, actually in the earlier '90s when I was using it on our projects, and then it's still legal today. Okay, and you'll see in here we're using types that look a little bit strange to you, and that's because the record is an in-out port. So each type has to have a resolution function, and the resolution function for standard logic wasn't quite the right one. Okay, so we have to have a resolution function. These are all defined in OS-VVM's resolution package, and this supports all the common types. We just append _max to the scalar types, and to make it portable for all tools, _max _c for the array types. There's also an _max, but it only works in fully compliant VHDL 2008 simulators. Okay, our long-term plan is to migrate this to VHDL 2019 interfaces, which is a very simple modification. VHDL 2019 says the interface is a record plus a view declaration, and a view declaration allows you to associate in and out with the particular record elements. Okay, at that point, you'll also be able to use it for your RTL design, but you need to make sure you go out there and, what's the right word? Tap your vendors in the shins to remind them, not literally, but figuratively, to remind them that you want these features, okay? Because many of them say, oh, we're customer driven, we're market driven. We don't look at standards until the market starts chanting about it. So I'm asking you to start chanting about it. All right, the transaction API is just subprograms, procedures primarily. And so we have one here named read. It does not conflict with any way with the predefined reads because we have our transaction record on the interface, and VHDL subprograms differentiate by types. Okay, so there's no way this will collide with anything that's predefined in VHDL. So step one, put things into the record. Step two, call this request transaction. This is one of our family of handshaking procedures. Step three, when request transaction finishes, if it's a blocking transaction, then we can grab our data. Okay, if it's not a blocking transaction, there won't be anything there yet. We support both styles though. Okay, now here's an observation I made over the years, and during the COVID shutdown, I was able to actually put it in place, which, I'm grateful for that extra time, although I'm kind of going stir crazy staying inside all the time. What we noticed is that some interfaces do the same sort of transactions. So if we look at address buses, there's Axie4, there's Avalon, there's wishbone, there's the smaller ARM bus APB for the peripherals, and they all do read and write operations, okay? And from the transaction level, they're really all doing the same thing. Now, how they do it, yeah, radically different, okay? But what they do and the information they need to be fed to do that, it's all the same, okay? And then we have streaming interfaces like AXI Stream, like UART, and that sort of thing. And it doesn't matter how they're formatting the data, whether it's going out bitwise or word-wise, they all do sends and gets, okay? They don't have addresses, all right? So what we've done then is for each of these, we've defined a record, just like I showed you, the address bus rec type. It's that plus a little bit more. And we defined a transaction API for it, the reads and the writes and that sort of thing. And then we did the same thing for the streaming models. So we have a stream rec type and a send, get, and check. And this is the basic set. So we support additional transactions, including bursting, including asynchronous type events that return immediately. So the blocking ones, that's the ones I'm showing here, work very well in the OS-VVM style test writing, but there's some folks that like doing single-threaded testing, and our asynchronous operations support that quite handily. And so they're, mind you, although they're saying they're the only ones that can do this, they're not. All right. Verification components. We have an AXI bus interface. Okay, so we have the DUT interface. In this case, you know, for the AXI bus, I represented it as a record because the AXI bus, it's really a mouthful. There are, I don't know, maybe 30 some signals on the interface. And, you know, devices may or may not actually be implementing them. They're different in size, but VHDL 2008 allows us to work with unconstrained arrays, so we can actually size these things when we're creating our test framework. And if you were to flip back to where I showed you that framework, you would see that I was working, I think I sized the transaction records because it also uses unconstrained arrays in it. Okay, so the transaction record is always going to be a record. Okay. Okay, so the verification component, it sits there patiently waiting for something. And so it starts up by calling wait for transaction. It can be, the verification component can be very simple, okay? So we call the request transaction into procedure. Here, its communication partner is wait for transaction. So when request transaction is called, that's the procedure saying, hey, verification component, I got something for you. And the verification component picks it up, looks in its record, and decodes it and does the operation. And doing the operation could just be calling procedures. But my preference is it's either simple enough that it makes sense to write the code here, which AXI is not, or it's complex enough that you have to write the code here because doing it via subprograms isn't practical. Okay. And when we get an interface like an AXI, here we have a transaction. This is a handler where it's actually operating on the interface. When we get to the AXI, it's a dispatcher, and it's handing it off to, there's 5 interfaces in AXI, and each one of them runs independently. So we hand off the write address to the write address handler, but we hand off the write data to the write data handler. And then we have a write response handler that's watching the responses as they come back, okay? And making sure they come back in the right amount of time and making sure that we actually get one, okay? And all of this is simplified by the OS-VVM model independent transactions because the read and write operations and the record are already defined. That means your focus as a verification component writer is just writing the behavior in the verification component. And that's no harder than writing a subprogram, but maybe easier because our community is used to writing RTL entities and architectures. Okay. So, and we'll talk more about that next time in the next webinar. Okay. In this webinar, we're going to go more into details of the test flow. So that starts with the test sequencer, test control, and on its interface, generally are records. So in this case, we have a TX and an RX, that's stream rec type, And that allows it to be, I think here it's a UART, but it could have been AXI stream. We don't really need to know what it is when we're building transactions. That's one of the interesting aspects. Okay, so characteristics of the approach. We've got the whole test in our sequencer file. So each whole test is an architecture of test control, and we have many of them. And when we look at the report, you'll see there's 50 some just for the AXI full verification components, and there's also likewise about the same amount for AXI stream. We have a control process. This is where we initialize and finalize the test, and we're going to walk through all of these. We have one process per interface. So the way I like writing tests is concurrent, just like your design. Now, it does complicate things. You have to do some synchronizations, but we've got that. So why not make it concurrent like your design? That makes randomizing things like we'll do here just a little bit easier. All right. Nah, a lot easier. Okay. All right, so our tests here are doing calls to transactions. Okay, so it's easy to see what's going on. If you understand a transaction API, for the most part, you should be able to understand the test. And OS-VVM's model-independent transactions make all the transactions APIs more similar. So like for the AXI interface, we do writes and reads, not AXI write and read. Okay, so that if you swap out an Avalon for an AXI, for some of the tests, you should not have to rewrite them. Okay, and in this environment, it's easy to write directed tests. It's easy to add functional coverage. It's easy to do constrained random tests, and it's easy to mix things because it's all transaction dispatched and randomization. It's all independent versus SystemVerilog, where sometimes you randomize and automatically dispatch a transaction. So then you have to have post operations and pre operations. That's insanity. Okay. Okay, anyway, we have synchronization. We have the synchronization here that coordinates the start of our test. We have the synchronization here that coordinates the finalization of our test. Okay. We also have error reporting in the form of alerts, affirmations. We'll see more of those as we go through the presentation, but what we're going to see here is in the finalization aspect, we call end of test reports. If you've been following OS-VVM for some time, this replaces report alerts. Okay, it does call report alerts, so you get the same report, but you get much more. Okay, so so again, because we have the common model independent transaction API, the calls for each API looks the same. Okay, and it's my hope that we'll be able to port tests from, if we're writing our tests right in some interfaces, be able to port to tests a little more easily, if not directly. Okay, our control process. What it's all about is initialization and finalization of my test. So I set my test name. I open my transcript. And mirroring says, send everything to a file as well as the console. Okay, I set up my IDs for my messaging and error control. Okay, I enable my logs and message filtering. So this is part of my message filtering strategy. And then we pause the control process until everything else is signaled test done. Or 5 milliseconds has gone by, and that's our watchdog timer. Okay, note what you see up there in the form of new ID is a constructor that calls OS-VVM singleton data structures. Right now, although it works in many of the tools, we're not using it declaratively. But in the next language revision, I've already gone out and put in the edits to make it legal to do that. But again, my observation is that Aldec tools, Siemens tools, GHDL and Synopsys tools all support that already. Okay. Or they missed that little error detection thing, or apparently didn't need it, so they didn't enforce anything there. Okay, anyway, next, OS-VVM makes writing self-checking tests easy. So one form of self-checking, I send on one interface, I get on the other interface and I check, did what I received match what I sent? Okay, so this is a very simplistic form of checking, and I'm checking it actually with the AffirmIf equal in the test bench. So AffirmIf is our base checker, and an AffirmIf equal is a specialized one that minimizes the amount of work we have to do. And because I called it with an ID that's TB ID, and I gave TB ID the name TB, it's going to tell me in TB, I received, if it fails, I received 8 and I expected 10. And it gives me the time it happened at. We are going to be offering in the future a format where the time prints first. We've got a request in that, and we've got a sensible proposal for an output formatter for it. Okay, we can simplify that previous slide just a tad by moving the checkers into the verification component, and just instead of getting and then checking that value, just saying, hey, check, this is the value I expect you to have on this operation. And internally then it calls AffirmIf. Now it's calling it against its model ID, so this is the UART receiver's ID. And by the way, generally in the verification components, most of the time I set the ID based on the instance label. We also have the ability to set it on all the OS-VVM ones. Choose if the generic for the ID is set, then use that, and otherwise use the instance label. The time that you want to be using in the OS-VVM VC, the time that you want to be using that generic is when you're using it in a for generate loop, because then all the instance labels are the same, and that causes some funny business to happen. That funny business actually has been fixed in the current release of OS-VVM. It kind of broke there early 2022, and then we fixed it, of course. So logging is OS-VVM's form of conditional printing. Okay, so the problem in testing is you can get flooded by the amount of information you got, and you want to instrument up your verification components so they can provide you the information when you want it, but you want to be able to turn it on and off. So we have log levels to differentiate between what we're working on, always, debug, info, final, and past. And we can also turn these things on and off on a verification component by verification component basis by using their ID. And we can look up their ID by its name. Okay, so we don't have to be passing that around. We just can quickly look it up in a test bench because we know their instance label, or we know their model ID name. Okay. These only print when they're enabled. All of them are disabled by default with the exception of always. Always is just on. Okay. And these print, the debug one wasn't enabled, so the only thing that prints here is the always one. Okay. By the way, you don't have to use the IDs for simple test benches. You just call these without the IDs. And the same thing that I'm showing here for the ID-based flow is available without IDs. It just doesn't say in TB, but for simple test benches, we don't need that. Okay. So for your RTL block test benches, but as soon as you get to the core level, it makes sense to be using verification components. All right. Randomization. So OS-VVM makes randomization easy, but the first thing you should be asking anybody is, why do I want to do that, right? Why do I want to do that? Well, okay, so let's look at a directed test of a FIFO. And this FIFO word count you see on this graph here is the number of words, an integer value, the number of words in the FIFO displayed as an analog signal. That's a really cool trick you can do in your simulator, although I should have also displayed it as an integer here, and I'll get to why here. So you can see early part of this test, I have filled up the FIFO, and then here I've emptied it again. So I did write and then read. And here I'm actually doing read and write first. So I put 2 words into the FIFO, and that's where I'm saying you need the integer count because you can't really see that. And so I put 2 words into the FIFO, and now I'm reading and writing simultaneously. I have metrics here. This is what I would consider to be manual functional coverage in the tracking, and sometimes that is indeed, even when we have the capability, we need it to be separate. So we're tracking that we got empty conditions and that we tried to read while it was empty. Down here, we fill it back up, and we check for the full conditions. So if we look at our verification plan, we've got a good check of our design. Okay, now with a constrained random test, we also get a great check of our design. You can see that we're getting empty, full, empty, full, but you can also see we're doing some great variations in between the empties and fulls. Okay, so we're running it over a wider space than the directed test. The directed test moves like a robot, right? Yeah, that's not going to always get the job done. So this allows us, constrained random allows us to do those variations we need to make sure that we've covered everything in our design. Okay, so the key benefit of constrained random is that we generate realistic stimulus in a timely fashion. And when I say timely fashion, that's all about writing the test. Of course, the constrained random test is likely to run longer than an equivalent directed test. But it's really ideal when we have a large set of similar items like mode, sequence, network package, and processor instructions. And that's why constrained random became a thing in the environment, because what was happening when it became really popular, well, networking was going crazy and we needed some methodology to help us out. Okay, so the first step in getting to constrained random is to have a randomization library. Okay, so OS-VVM provides a randomization library, and you can either call it positionally or you can call it with named association. And named association, of course, adds a greater degree of readability, but we can also be sensible and make the calls short when we need to or when we want to. It's okay to know randint has a min and max of 0 to 15. So within our randomization capability, we have a range. We have a range with an exclude vector, and that exclude vector is an integer vector value. We have a set that we represent. So randomly pick a value within a set. We also have exclude values here. You could view the exclude value as a subtract value if you wish. We can do weighted randomization and weighted randomization with excludes. The weighted randomization, the way it works, the simple form here is all we're specifying is the weights, 7, 2, and 1. And generally, I make the weights sum up to 10, 100, or 1,000, because then I can read them as percentages. Otherwise, I'm like, what does it mean, right? And so here, they sum up to 10. So the first value is going to be generated roughly 70% of the time. And the first value is, if I specify it as a literal like I have here, or an aggregate like I have here, is going to be 0, and then 1, and then 2. And it's all comes down to, it's an integer vector, and the default range for integer vector is 0 to something. And that changes when you work with types like UFIX and SFIX, where they have negative values also for the indices. And so they start at the leftmost value of the type, which is very ugly with those types. Okay, we also have a form where you specify the value as well as the weight. Okay. By itself, this is not constrained random. This, again, is a randomization library. So what we have to do is learn code patterns, and that's one of the things, by the way, that we teach you in the OS-VVM class that Synthworks teaches. So here, I'm using distint, and I'm going to be generating the values. Well, there's 5 values here, so I'm generating the values 0 through 4, okay? And I'm doing 70, 10, 10, 5, 5, so that's my distribution. So 70% of the time, I'm going to be picking a nominal case. And if I'm sending things on a UART interface, I might want to, the nominal case is not going to inject any errors, and my data value is going to be, it's 8 bits, so it's going to be 0 to 255. Okay. My stop error, okay, so I have a code for injecting my stop error. It is encoded standard logic vector, by the way, but it could have been anything. And then this is where constrained random comes into play. I excluded the 0 value in the data. Why? Well, simply because if you're doing even parity on a UART interface and you transmit 0 and you say stop error, well, it's not a stop error anymore. It's a break error. Okay, it presents as if the line's been disconnected. So we have to exclude that value from this set. We'll include that value in the 4th case where we're generating break errors. Okay, and then here at the end, we're doing the transaction, but that's not the only way to do this. Okay, in the first case, we could be doing something that, say, transfers 2 packets, and then the next one transfer, in case 2, we might be transferring 3 packets, and so on. So there are different ways to do this. Okay, so what we have here then is OS-VVM's methodology for constrained random is randomization plus code plus transaction calls, and that's how we implement things. Okay, so how do we set this up in our test bench then? Well, what we'd been doing before was we set the receive side to follow the transmit side. That's not really an easy thing to do here. It is, we can do it reliably, but it's tedious and potentially error prone, so we don't want to do it. Instead, what we're going to do is introduce OS-VVM's generic scoreboards. Okay, a scoreboard really is a FIFO with a checker inside, and a checker has some flexibility because we provide it with a generic subprogram to determine whether they match or not. And for a UART, that's important because when we're injecting a break error, we only expect to see the break bit. I don't care what the data is anymore, right? So on a break error, I don't care what the data is, but if it's not a break error, I care about everything. Everything has to exactly match. All right. So the scoreboard is a FIFO plus some methods, okay? And it handles small data transformations. That's via the match function. It handles out of order and drop values. Okay. So it's a generic. We'll see how they work with that in a second. And then this is the new API. This is the singleton API. So we just call regular procedures and functions. Okay. That's the fun stuff. Okay. So we have in our library scoreboards for standard logic vector and scoreboards, and scoreboards for integers. Okay. So this is all standard part of the OS-VVM library. But you can also instance your own as you need. The only thing to know is the end of test reports automatically looks in these and sees if you have scoreboards. But if you instance your own scoreboards, then you're going to have to do the reporting yourself, okay, for those. All right, so using OS-VVM scoreboards is easy. We create a signal, and then in the control process, we can call new ID. Again, long term, we're going to do this initialization and make this a constant and do it in a declaration. And again, many of the tools allow that already. And then using a scoreboard on the sending side, we do all the fancy stuff, the randomization, and then we push our values that we're sending into the scoreboard, and then we send. On the receive side, it becomes very, very simple. And it's just get and check. And the check here is actually checking the value that get received and putting it into the scoreboard. And you can see here, I've kind of changed up the problem a little bit so that we're sending both the data and the operation value, and we're checking the data and the operation value. So we've made it the full complete form of the UART then. Okay, so the next thing we might need to do is track some functional coverage. Okay, so functional coverage is simply code that tracks whether things in your test plan actually occur. So we're watching requirements, features, and boundary conditions. And why do we do this? Okay, so we need to make sure that like a random test actually did what we claimed it did, but also for directed tests, as our complexity increases, it's a valuable thing there too. Okay, to make sure we really did what we set out to do, that we observed it doing what we set out to do. Because it's just like we started. When we started FPGA design, we just wrote the code, programmed the board, because the code most of the time was simple enough to do in the FPGA, and yeah, that's going to do it, and then test it in the lab. That was fine. But then we moved to simulation because things got more complex. But this is the next layer of complexity. As our designs get more complex, functional coverage becomes an insurance plan to make sure that we really tested everything we meant to. Okay, we have two forms. We have item coverage, or others call it point coverage. Depends whether you're an E or a SystemVerilog person. I like the E terminology because the SystemVerilog terminology, there's point coverage and then there's coverage points, and they're different things. So that makes that word nonsense. Okay, what we're doing with item coverage is we're tracking relationships within a single object. So we're binning, right? We're looking at a transfer size, and we're doing small transfers 1, 2, 3, and then we're looking at big transfers 253, 254, 255, and then we're looking at some mid-range of the transfer. Okay, so that's one application. We track relationships between multiple objects. Okay, it has each set of registers. So we have an ALU. It has two separate inputs. Each input can select from a number of different sources. Has each possible source from input 1 been used with each possible source of input 2. That's cross coverage, and it's correlating independent things. Okay. Now, why not just code coverage? Okay, code coverage tracks what's happening in your existing code, but it misses anything that's not in the code. Features, the binning that we're doing above in item coverage, the correlation of the items that we're doing above in cross coverage. Okay, and there's a few other things, nitpicks that I have about code coverage. But at the end of the day, code coverage is important, because if your code coverage isn't 100%, you haven't done everything. Okay, that it clearly says. Okay, so coverage package is all about simplifying the definition of coverage, the collection, and the reporting of it. Okay, internally, it has a data structure and of the coverage, and then it also has some configuration parameters that it stores in there for each different coverage model. It is a singleton. The singleton API defines what our coverage capabilities are. This is a brief set of them, but rather than talking about them here, we're going to just dive right into the examples. So with a UART, we want to be watching, did I get no, break, stop, and parity errors? Did I get just a parity error? Did I get just a stop error? Did I get a parity and stop error? And did I get a break error? So I need to be able to check for things like this. And so the way we do that is, rather than looking at them in bit values, we could do it as cross coverage and look at them as bit values. I would only do that if I had to. Instead, my preference is convert them to integers, okay? Because then we're just doing item coverage. It's one thing versus a set of things. But we do the set if that's what we had to do. So we create our ID, we initialize the data structure, just like we're doing with Scoreboards and the alert log IDs. It's all the same overloaded function. It's just doing different things for different contexts. One way VHDL overloading differentiates is by the return value functions, and these all have a unique return value. Okay, so that's how we understand what we're working with. So we define our coverage model. We're not going to have a chance to dig into this deeply here, but we define each bin, and then we collect our coverage. It's really that simple. And people say we need the language to define things like, we need SystemVerilog because the language defines things like that. I disagree, okay? Because functional coverage with OS-VVM is just as concise as language syntax, and that's really, at the end of the day, what we're looking for. And also, it's more flexible than what you do with SystemVerilog, because all SystemVerilog coverage is defined in the declarative region, where here it's defined in the code region. That means you can use any sequential construct to help you, including like if statements, and create conditional coverage. So that's the capability that they don't have. Okay, so another thing we can use our coverage for is randomization. Okay, so we can randomize across a coverage object. So we're setting up a similar coverage object to what we did before, except now we're adding additional information. And the important one is we're adding a name, which is nice because it's going to print that name when we do our reports. But we're also adding here a coverage goal. Okay, SystemVerilog calls it an at least value. So OS-VVM and E calls it an at least value. And since they both agreed on something, I decided rather than calling it goal or coverage goal, that we should call it at least also, just for some commonality between things when it's possible. Okay, so if somebody did a study of SystemVerilog, that's what they would have named it. All right. So what do we do with this then? We've defined a coverage model with the randomization weights. Then we just say get ran point from our coverage model. And this is randomly selecting our mode, okay, with the constraints we gave it. And then we're doing the same targets we were doing before. The actions don't change, just the target value is. The value that comes out is going to be the value we specified. the 1, 3, 5, 7, and then the 9 through 15. We have to add something to collect the coverage. Okay, the other aspect here is to be able to collect the coverage here, you have to be careful. Okay, you have to know that when I say send, the only thing that this can do is do that operation, and that it doesn't inject any randomization into that. If it does inject randomization in the verification component, then you have to create a monitor that observes the output of the verification component to collect the coverage instead of doing it here. Okay, and because we use the singleton, passing around either our coverage model or our scoreboards or anything else is just like passing around an integer constant. Okay, it's not like passing around a shared variable of a protected type. That's hard, and without 2019 it can't go through entity interfaces. Okay, so here another way to say what we're doing with our intelligent coverage randomization is we're doing a dynamic coverage driven randomization, and we're using the coverage goals as our randomization weight. Okay, now be careful with that word coverage driven randomization, because SystemVerilog also uses it, but they're not doing dynamic, they're doing static. They're doing an analysis after simulation's complete. And it's almost, I kind of disagree with their usage of that word in that case. But yeah, that's enough to differentiate. So protocol checking, we do alert if. This collects up all our errors, and so we're just looking for bad conditions that happen. For example, in a RAM model, if we have chip enable, write enable, and read enable all active at the same time, well, you can't do a write and a read at the same time. Okay, so that's an error. Okay, in the OS-VVM packages, in randomization, if max is less than min, that's an error. Okay, and alerts can be enabled and disabled, but generally it's not just this simple to turn them off. They're still going to count as a test error. This will stop their printing, but they still count as a disabled test error. You've also got to turn off the disabled test. Hey, VHDL is used in a safety critical environment. We make it very hard, if not impossible. If you're doing due diligence, you will not miss the fact that there's a disabled alert in OS-VVM. Okay, and then we also have the capability to stop the simulation. So like alert stop count. Okay. Test finalization. We're done with our test now. We were sitting at that barrier test done. Everybody else at the end of their test cases, call, wait for barrier test done, and then it completes. Okay, so a barrier completes when all the partners who are going to call it end up calling it, and they all release at the same time. In the other processes, they just hit a wait statement at the end of the process. This one continues, and it says, hey, is the current time greater than or equal to 5 milliseconds? Because if it did, the test failed and I need to inject an error, because maybe the test failed so bad that it didn't get to any of the checking parts. Did the scoreboard, is the scoreboard not empty? If it's not, then I want you to report an error. Okay. Did you do any checking? If you didn't, report an error, because down at the end we're going to say pass failed, and it's not good form to say passed if you didn't do any checking. And in here we're actually doing some checking, so if we knew we were doing this, we could have skipped the above, but we're checking our transcript file matches a previously approved transcript file. Okay. And then we do our end of test reports. Okay. Now I make it a practice call standard env.stop with my error count, but a lot of the tools don't give you a mechanism to report that. So that's not 100% necessary. In fact, the only one right now I know of that does is GHDL. Our reporting, our simple form of reporting, end of test reports, and we get, this is the report alerts report. Okay, this is the first level of reporting that we do. Okay, but we'll talk about the second form in a second. The other thing OS-VVM brings to us is scripting. Okay, and the intent of OS-VVM scripting is that it's simple. Okay, it reads like a text file, but it's Tickle. So it has the power of Tickle there if you need it. But it's okay to hate Tickle, right? Because most of the time we make it so you never, ever have to use Tickle. Okay, and one of the ways we do that is within a given script file. You might call it from somewhere else. We'll call it with include. You might call it from somewhere else, but every reference in that file is relative to the location where that file is at. So you don't have to do any gymnastics, tickle gymnastics to determine, oh, where did this get called? What's the relative path to this from where you called it? No, OS-VVM takes care of all that for you, at least if you're using the OS-VVM commands like analyze. Okay, we also remember things. You tell it the library, that makes that library your default library. So when you call analyze and you call simulate, you don't have to tell it the library again. That's nonsense. Okay, we make code coverage easy. And we also remember the language revision that you set, but we set 2008 by default because that's what you need for OS-VVM. Okay. And you run things by calling build. So this is what you call from the simulator command line. In the third presentation, we're going to be talking about reports and talking about scripting, so I'll get more details into how this works, but there's also the script user guide in the OS-VVM documentation directory that'll also walk you through using these things. And if you're looking to try out our demos, that's where I'd go to start reading on how to run the demos. Okay, so we create these reports, and these started coming out in late 2011. So we called it the October release, but it was really the early November. Okay, so and it's changing, it's evolving. So if you looked, the first thing we create is our build report. Okay, and it tabulates. Okay, it passed. There were 520 passing tests. 4 of them were skipped. We don't count skipped ones. As a safety check, we also track, did any analyze fail? Did any simulate fail? This is a new feature. This is going to be out at the end of the month. This is going to be part of the 05 release. And by the way, we've been doing smaller feature releases about monthly. Okay. This tells us what simulator we ran in. This tells us how long it took to run. This tells us the simulator name as well as the version. Okay. We provide an HTML version of your transcript. Also, if you ran it with code coverage, we for each test, we collect code coverage. We merge all those together as we go through each test suite, and then we merge all the test suites together, and then we produce the report. So you can then, the vendors provide you with an HTML report, and you can then take a look at that, and this will show you the code coverage over this set of tests. I think I just ran a demo suite, so we're not looking for 100% coverage here. And then we have all of our test suites. So OS-VVM breaks our test cases down into test suites. We have an AXI4 Lite test suite and our regression suite. We have the AXI4 Full. We have the AXI Stream. Testing the verification components. The bottom ones are testing the OS-VVM library. Okay, and this summarizes how the suites did. This summarizes how each test case does. So as we go down each level of hierarchy, we basically look at the top. It all passed, we can ignore it. Okay, something failed, we look, okay, it was in this test suite. Okay, in that test suite, and these are all links. So you can click, oh, it happened in the virtual transaction interface. So we immediately jump down to that context, right? And then, oh, it happened in this test case, in one of the test cases. Let's jump down into the detailed test case for the AXI memory read-write demo. And because it has some coverage, the coverage wasn't intended to be 100% covered. In here, we have our alert reports, our functional coverage reports, our scoreboard reports. These are all links into this file. Links out of this file is our simulation results. Here, though, I'm able to do more. This link to the simulation results, oopsie, that one didn't go well. For some reason, it didn't HTML. Oh, I know why. Sorry, I ran it with some new stuff that I'm testing. And yeah, I'll show you a different one. Let me pull over the other one. Come on. That's odd. This is just the report without the functional coverage. Same thing. I ran it earlier yesterday before I made some experimental changes. So if I click on the link to the simulation results, this is what I get. So I get an HTMLized version of the results of that simulation run. And it actually jumps me to that exact simulation run. Why is that important? And by the way, any place you see these triangle things, if the triangle is pointing down, you can close it and go through things. This is the OS-VVM regression suite. You can see, I can see what's going on here pretty good from a high level. Mind you, the reason we HTMLized it is because this file is probably, and we just scanned through the whole thing, right? It's probably bigger than 180,000 lines long. Good luck with that if you have to scan through it and search through it. That's just drives me batty. We also have a link. Anything that you open with transcript open, we have a link to it. You'll note that our detailed alert report is more comprehensive than the report alerts report. So this is the real go-to one now. Also, we have our, if you did coverage, basically when you call report alerts, it goes out there and says, hey, got coverage? And if you do, so it asks the singleton that. If it does, it iterates all the coverage models that you have. So you don't have to think about, oh, I've got this coverage model, I've got to print it. No. That's too much busy work, and I'm too lazy to do that. It automatically happens for you for all your coverage reports. Also, it happens for your scoreboards if you're using the ones from the OS-VVM library. So this test was kind of an oddball test in what it was doing with the coverage ranges. So it didn't make any sense to label them, and it doesn't make any sense of, there's not a lot of point to what it's doing there. But we also get our scoreboard reports here too. Okay, so just kind of wrapping up on that thought, the reports are really something much more than they used to be. There we go. Okay, so the slides in between there that I just skipped over were just showing you exactly what I was able to show you with the live demo, and I think the live demo is quite a bit better. How do I start learning OS-VVM? Well, there's two focus points, and I'm showing you one of them here, osvvm.github.io. This is a set of HTML pages that we've generated that give you links down in the documentation. But also, if you go to the github.com/osvvm/documentation page on the website, right? On the website, it's going to give you an HTML rendering of the README file. And the README file also has similar information, but in one single thread of the file. So a little bit more terse. Then to get OS-VVM, two ways. One is with git clone. You got to use recursive because we use submodules, okay? And then alternatively, you can get a zip file from osvvm.org. The thing I'll say is if you want the freshest, newest stuff, it's on GitHub. We do monthly releases, so right now, when we start traveling it again, it'll probably be every other or every third month, something like that, every quarter releases. We'll be doing more granularity, but for now it's monthly. So osvvm.org is getting updated frequently. So if you start your simulator and you go to the directory that contains OS-VVM libraries, the first thing, and I wanted to show what OS independent, so I figured I'd do it from the simulator. This is Tickle, file make dir sim, and then cd into sim, and then call the scripts. You need to start up the script. So this is good for Riviera Pro and also the Siemens tools. For all the other simulators, see the script user guide.pdf, and it'll walk you through how to start them up. It's just a very, very small variation. Active requires you, for example, to turn on tickle mode first. And then we call build. And this set of builds will build the OS-VVM libraries. The next one will run all the tests. Within the OS-VVM hierarchy, we have run all tests and run demo tests. And most levels of the hierarchy support that. So if you run all tests at the OS-VVM libraries directory, it's going to run all the verification component regressions. Okay, if you want to run a selected set of them, you run the demo tests. Okay, and those might change from time to time. Sometimes it's inadvertent because I add things to it. I change it as I'm debugging and stuff. Okay, hey, we're at the end. So let me wrap up here. All you need is OS-VVM. We have the framework, the utility library, the component library, and the script library that's going to help you get your verification job done. And benefits, you can adopt it incrementally as needed. The tests and the verification components can be written by RTL engineers. The tests are readable and reviewable by all. It's powerful and concise and rivals other verification languages. And this is something SystemVerilog doesn't do very well, so I wanted to focus on it. We support mixed approaches such as directed, algorithmic, file-based, constrained random, and the last one, intelligent test benches, or our intelligent coverage randomization. Okay. In this webinar series, this was part 1. We have part 2 where we're going to talk about verification components and talk about why I think our methodology that goes straight to verification components is better than a methodology that suggests that you use subprograms instead. So our light approach really is to use the model independent transactions and go right to verification components. My thoughts there are your RTL engineers who you might want to spin up on verification already know how to do entities and architectures. They don't need to bother with subprograms. And the OS-VVM methodology makes that possible. Okay. In part 3, I'll talk more about the test reports and the simulator scripting. In part 4, I'll talk about the advances that we've made in our verification data structures and why OS-VVM is a lot better than the other VHDL alternatives out there.
Right. Now we will have a Q&A session with Jim. So before that, I would like to recap on the points that were discussed by Jim. And by the way of summary, they are: VHDL is still #1 for FPGA design and verification. We learned about OS-VVM, its framework, and its libraries for verification components, verification utilities, and scripts. You can upgrade your current VHDL test bench and models incrementally. Test and verification components can be written by RTL designers themselves. Tests are readable and therefore reviewable by all. Now, let's look at the questions that we have received. Plus, we have received some by email ahead of today's webinar. We don't have much time now left, but you are welcome to use the question panel on the right-hand side of your screen. Here, Jim, there are some questions for you so far. Are you okay to answer them?
Please, I'll run as long as people want to stay.
Thank you. Right. How do I learn OS-VVM?
Yes, so I referred to the web link, osvvm.github.io. If you want to learn it on your own, we've got you covered. We've got a lot of documentation. You should just be able to plug and play with the documentation. But if you want to learn things fast, Synthworks does training on OS-VVM, and we're experts on it. We're going to give you deeper insight than you'll get necessarily from just reading the documentation.
Thank you, Jim. One of the audience wants to know, wouldn't it be easier if VHDL would support calling procedures in other verification modules, such as Verilog supports by default? This would eliminate the resolution functions on the records. So this question is with respect to your slides 10 and 11.
Yeah, no, I understand exactly where it's coming from. I understand what your issue is, but it's already a solved problem in OS-VVM, and it's integrated into our model independent transactions. And we're not even making you, unless you need to go outside of the standard things that we've already provided for you, the model independent transaction, the address bus, and the streaming. If you don't have to go outside of those, you never have to write it yourself. Okay, so you just focus on writing your verification components. Also, with VHDL 2019, which ALDEC, mind you, has already implemented, so the VHDL interfaces makes all of that magic that we did with the records easy stuff. Okay, it makes it easy stuff, and so yeah, it shouldn't be a problem at all. So and I don't like what Verilog does there. It's kind of confusing because what you're doing when you do that, when you drive a subprogram that's defined in a component, you have to trace an instance path to that component, which is a very interesting thing to be doing. Okay.
That's good to know, Jim. We use MATLAB Simulink for implementation. MathWorks suggests using SystemVerilog for testing, as it can use DPIs, C components generated by Simulink. Can OS-VVM support that?
That's, and I see two questions related to this too. And that's something that we would have to look at. We're not currently connecting to any DPI type things, but that doesn't mean we can't in the future. And if, what I would encourage you to do is either send email to me directly about what you're looking to do there, or submit an issue on our issue page on GitHub, or submit a question on osvvm.org. So that's another place we have forums on osvvm.org that we can work with you on.
Thank you, Jim. Can we use OS-VVM library in Vivado tools?
Yeah, that's a work in progress. XM is not quite up to speed for anybody's VHDL verification methodology that has any level of sophistication at this point. So at this point, what I would say is, with Vivado, you're going to have to go to a third-party tool. But just like they're working on SystemVerilog, they're also working on VHDL. So.
Right, because we have not much time left, so I will be quickly asking you few more questions, if that's all right.
Oh, it's the speed round.
Are verification components really as easy as the sketch you showed?
If they're blocking verification components, definitely. But for non-blocking ones, and we're going to go through that in the next webinar. So that's a great place. Come back to the next webinar and we'll be able to answer that in detail. But also, it gets a little bit more interesting when you have dynamic dispatch. But for dynamic, basically what you have when you have the interface has independent pieces of it, like AXI has so, but we handle it well. It's just harder, but it's harder any way you do it. Okay.
Right, sure. Thanks, Jim. Now, another Simulink question. We use MBD approach to code out from MATLAB and Simulink. From this, we can export verification components that integrate with UVM. Is there a way we can use exported elements from MATLAB Simulink as part of OS-VVM verification components?
Yeah, that's the same question that was before. It's a very similar question before.
Yeah, sure.
I would be more than happy to have a chat with both of the parties there and see what needs to be done, to try to explore what needs to be done and see if there's something possible there, because that would be a very, very interesting thing to be able to do.
Right. Where can I ask more questions about OS-VVM if I need to?
Yeah, at osvvm.org, we have a OS-VVM forum where you can ask questions, and either I answer them or someone else answer them. The nice thing about asking questions there, by the way, rather than sending me a direct email, is that if somebody else has the same question in the future, they'll be able to see it in the forum without having to ask the question again.
That is great to know, Jim. Now, where can I learn more about OS-VVM functional coverage, scoreboards, FIFOs, and memory models you just talked about?
Right. So, and what's really cool is there was a big update on those last summer, in summer of 2021. So I'll be talking about that in the 4th presentation. So please come back for that, and we'll get into the details there.
Right, so we will be closing this question and answer questions. We didn't have much time to take a couple of them, which are still there. We will surely come back to you. So this is now all that remains for me is to thank you, Jim, for your presentation. Better FPGA verification with VHDL Part 1, OS-VVM, leading edge verification for the VHDL community. We have part 2 in the series, which will be held in 2 weeks' time on June 9th, and we will look forward at faster than light verification component development with OS-VVM. Part 3 will be held a week later on June 16, and we'll be discussing OS-VVM's test reports and simulator independent scripting. The concluding webinar of this series will be held on June 23rd, and we will be looking at advances in OS-VVM verification structures. To know more about our EDA solutions, we invite you to email us at sales@ldec.com or visit our website, ldec.com. It is also from our website that you can view recordings of previously held webinars and register for upcoming ones. We also invite you to follow us on LinkedIn, where we'll be posting news of upcoming events and providing advice and guidance. I hope this concludes our today's webinar. I hope you have enjoyed it. I'm your host, Nomita Goswami. Thank you all for joining us today, and a big thank you again for Jim for presenting. Thank you and goodbye.